PT.
Good. Now we see some alpine mountains.
Right. I'm just trying to manipulate
Okay. All
my
right.
screen a little bit.
Okay.
All right. I'm very happy to see everyone here. So this is actually my second colloquium, and it's like I have to have one for my PhD, and I enjoy it. And Dr. Vic was my awesome PhD supervisor. And then long story, make it short. I was doing coastal geomorphology study before whenever I was in Taiwan. And so I come to UF and I say, well, let me do some fancy statistic analysis study. So I decided to working with Dr. Vic. And then after that, I got this opportunity to be able to working with Dr. Masa as a postdoctoral fellow. And I really enjoyed this whole process. And yes, Dr. Masa, she is a host of Colloquium for this semester. So I have to, and I want to have a presentation for everyone to talk about what's my postdoctoral study been working about. So this presentation today is part of our project. So it's more my current study, and Dr. Masa also helped a lot with the entire study. So I'm just going to repeat my title again, just in case people don't remember already. So the title is Vegetation Regrowth on Point Bars in a Disturbed Coastal Plain River. And yeah, just call me Chen. I guess should be few people who can pronounce my name correctly, and I'm also very happy there's only one Chen in the departments now, so you guys don't get too confused. All right. So like I mentioned before, well, actually Dr. Mosa give you guys some really brief introduction about what's going on about our project. So this postdoctoral research is being focused on the impact and recovery from the anthropogenic activities for the Apalachicola River in Florida. And before I dive into the entire analysis study, I want to have a really brief introduction about Apalachicola River, because I don't know. Oh, I'm the one talking. Is that also showing? And I'm not sure if anyone ever been Apalachicola River. It's a really beautiful river. So it is part of the Apalachicola Chattahoochee Fluent, and you can call it ACF Basin. And this ACF Basin is basically across 3 states, which is Alabama, Georgia, and the Florida state. And then the entire Apalachicola River is basically in Florida state. And the total area of the entire ACF basin is about 15,500 square kilometer. And the total area for the Apalachicola River is only 2,900, which is about like 5% of the entire ACF basin. And this entire river is located on how we call the coastal plain area of the US. And the mainstream is just a really one channel, a meander form, flow through the entire floodplain, And whenever it's in the low floor, it's like one huge meander river. But whenever the water, you got the rainfall, the fall water going up, it start connecting with the floodplain streams and eventually fill the entire floodplains. And it is also one of the hotspot for the biodiversity hotspot in South US, and it's a home for many endangered species. So I would say this Apalachicola River have really high importance for the ecosystem. All right. So human beings actually been living in the Apalachicola River for a while, but not until 1950s. Fedora dams, they start building in the 1955. And the US Army Corps of Engineers, they also come out with this really ambitious navigation project. So the main goal of this navigation project is they want to make sure they can maintain this navigable channel for cargo boat can go through the entire river from Apalachicola. So Apalachicola is actually a town, a name of the town in the in the exit of the Apalachicola River, right? And so they want to bring a cargo, they want to bring a cargo from Apalachicola upstream to Columbus in Georgia. So in that case, they have to keep this navigable channel so they can make sure those cargo boat can go through the entire river safely. So one of this historical photos showing the barge boat in Apalachicola River. And here is a profile showing them how the crop decide to, they want to make sure the depth of the channel is more than nine foot deep and the wide is 100 foot wide. So those cargo boat can go through the entire river safely. All right. So most of the dredging materials, so once you dredge your materials, because you have to maintain the good depth for the cargo boat to get through. So the idea of they want to keep the sediments still in the floodplain system. So they come up with the idea, say, hey, let's keep the sediments in the floodplain. So here is a map on the left-hand side. You can see I already modified it. I kind of color it. So you can see here, so many disposal sites, they're basically on the margin of the channel or actually under the water. And there's several disposal sites on the floodplains. So perhaps the disposal site number 40 is perhaps the biggest site in Apalachicola. And we have published a paper to study the spatial and temporal changes of the specific site. And here I want to show you a fancy website. Yes, fancy. All right, so this is the DOI as a paper is published early this year. So I just want to show you quickly how you can, it's like an interactive website, you can play with it. So here's the elevation. We built 4 elevation model from 1960, 1980s, and 1988 to 2007. So you can see how the dredging mounts being changes. And this is quite cool. You can play with the, the compare mode. So you can see what's the difference from the 1960 to 2007. All right. So anyone who really interested in this, please read that paper. All right. Just small PR. All right. So what's the impact? So the impact of this whole dredging and the dam building activity actually lead to water level decline, and there's a channel width within, and also there's one really obvious things happening is a point bar enlargement. And before I dive into the point bar things, I want to have really brief introduction about point bars. So point bars basically mostly occurs on the meander bands. And here's the figure showing, I don't know if you can see the mouse. So this is on the deposit side of the meander bands. And whenever at lower water level, you can see a huge bar surface showing up. And this point bars also migrate with channel. Whenever the channel migrates, and the point bar will also kind of move with it. And the previous studies have shown, they compared the era photo in 1940 to 2004. Well, actually, this figure is showing 1941 to 2017. So just saying from 1940 to 2004, the point bar area has increased 263%. And just by looking at this era photo, you can see the channel is much wider, and you can also see a lot of point bars show up because this photo is actually taking in a kind of lower water situation. So you can see a huge point bar showing up on the era photos. All right. So eventually this navigation project actually become the most expensive project in the South US because you have to spend a lot of money, keep on dredging the sediments from the river bottom. and they actually don't have too much cargo traffic. So it's like you spend a lot of money to maintain this channel, but you don't gain too much money because there's not too many cargo boat get through the river. And especially this kind of dredging activity is really intense in the Middle Reach, which is actually the study area I'm going to focus on today. And then, I mean, part of the reason the Middle Reach have a more intense dredging is because they have some of the problematic area have a higher riverbed elevation. So they need to keep on dredging the materials from the channel. So in 2002, finally, and then they figure out, okay, this is not going to end well. So they decide to stop the dredging activity. So since then, we're going to call this as passive recovery time. So there's a study compared two pair of aerial photos at the first and the 30th percentiles after decades of dredging cartels. And the box charts actually showing how the area of sandbars changes decades before, well, earlier ending of the navigation and later decades after the dredging ending. So the result is concluding there's approximately 50% of the point bars being recovered. And the biggest reason for the point bar being shrinking, I mean, what I'm here I'm saying the point bar is shrinking or smaller is because you have a lot of riparian vegetation growing on the point bar. So that's why those bar sizes are getting smaller. So here I want to say the regrowth or recolonization of vegetation as part of the recover process in Apalachicola River. So here's the idea. So now we know the river is slowly recovered. And what if we want to do something to increase the rate of recovery? Well, not as ambitious as, as this GIF showing, but to help the Mother Nature to speed up the recovery process. We want to know how much, how quick, and in what ways this river recovered before we want to conduct any active restorations. All right. So part of my postdoctoral studies, I've been focused on how this riparian vegetation regrowth, re-established, and regrowth on the point bar in the Apalachicola River. So there are several well-established researchers who already study how the vegetation grows in the riparian zones. And perhaps one of the most famous one is Cohen Brett et al. 2007. And their research team, they review lots of study, and then they come out with a conceptual idea about there are 4 phases of biogeomorphic succession of those riparian vegetations. So among 4 phases, just 4 phases. We're especially interested in the biogeomorphic phases. Let's say the phase 3. So it's the most dynamic phase, which has multiple variables influence each other. So here's the figure showing there's one of the study, many people using this kind of theory to do their own study. So this is just one example. So one of the person using this biogeomorphic succession study. So here's a graphing showing in the stage 3, which is what I've been mentioned about the biogeomorphic phase. So this is a phase whenever you have a young tree growing up in a phase 4 is eventually become a mature forest. All right. So in Apalachicola River, so Mosa et al. 2020, and we have suggested a conceptual diagram showing how the hydrologic, geomorphic, and the ecological factors or drivers influence the Apalachicola River and how those factors changes among the space. So on the top of the graphic, you can see how the different factors have a larger or smaller influence in different locations of the point bars. So for example, if you look at the brown color for the geomorphic one. So it's basically have the most influence on the sandbar surface. And so for the interaction between factors, for example, the flood water and the water level can not only, so whenever the flood come to this sandbar area, it can uproot a lot of seeding, but it's also very important for new growth because they need to be able to reach the groundwater. And as I mentioned before, this interaction between these factors are really dynamic. And so far, there's really few studies focused on building a quantitative model to understand this dynamic relationship in a large low-lying disturbed river like Apalachicola River. All right, so this is actually the, I'm going to present sort of two study. So this is the first study. So after I explain the background behind the vegetation regrowth in Apalachicola River. So there's manuscript we are trying to developing now, hopefully being able to submit it soon. It's about the drivers behind the vegetation regrowth on point bars in the middle of Apalachicola River. Okay, so the main purpose of this study is we want to find out what is the drivers behind the vegetation regrowth or recolonizations on the point bar in study reach, which is the middle reach, part of the middle reach of Apalachicola River. And we apply logistic regression model and the random forest model to determine which factor have higher degree of influence or have the higher importance to the recovery process. So based on the previous study and the data availability, we select 8 variables. Like I mentioned before, the dependent variables will be if the areas recover or non-recover. But for the dependent variables, there's 8 of them. So if you can separate into 3 types. So the first time is geomorphologic. So we use a digital elevation model to create layers for slope, roughness, and aspect. And we also apply a hydraulic model we developed in the previous paper, so which actually provide the flood depth, velocity, shear stress, and stream power at the bankful water level. So what is the bankful water level? It's about 2,000 cubic meter per second. That is a bankfall whenever the waters basically cover the entire floodplains, 96 percentile, yes. And finally, we only have a one ecological variable, which is the distance to tree line in 1999, which I will explain a little bit more about why it's 1999 tree lines. So here just a map showing the study area. And like a figure 8, I still put in the ACF basin and where it is. And the study area is part of the middle reach. So it's in between the river mile 40 to river mile 63 or 64. So there are 27 major sandbars in study reach, but we only select 15 point bars out of 27 of them, which I will explain later. And if you, so there's a figure CDE is actually showing where the sandbar is. So only marking those selected point bar with the brown color. All right. And of course, you want to see how the point bar looks like in the real world. It's going on. Okay, here I want to show you a field video I took on the point bar, like you standing on the edges of the point bar. So this one you can actually see on the another side of the bank. There's a lot of erosion happening, so you can see a lot of tree actually falling because that's the erosion side. And the area I'm standing on to taking the video is actually the deposit side. So you can see there's a lot of fluvial sediments on the bar surface, and the boat just get through. That's a boat we use. So we really appreciate Riverkeeper. So they are the one bring us everywhere in this river. All right, it's a lot of fun in the field trip, got to say. All right. So here's another one. It's actually from another direction of the point bar. So let me play this. Here you go. So here's another short video showing how a point bar looks like from the edges of upland forest. And this is one of the largest point bar in the Ecological River. And most of the point bar surface are flat, sort of flat, and you can see a lot of sediment. And you can also see the tree line, which you actually need to go back to the beginning. Okay, so here's the tree line, what I mentioned before. And then you see a lot of small, new, young growth really close to the current tree line. All right. Close. So here I want to show you how we make the sampling for our models. So first of all, like I mentioned before, we use this binary independent variables, say recover or non-recover. So in order to define the recover and non-recovered zone, recovered and non-recovered zones, and we select two sets of area photos taken in the 1999 and 2019, actually covered 2 decades, 20 years of the recovery. And the reason why we pick up 1999 is because that is the area photo we can find most close to the end of the dredging. So we are going to say, okay, the 1999 photo is quite close to before recovery. And 2019 is 2 decades after recovery. And we digitize the tree front lines and the point bars of this 2 years area photo. And you can see in the figure C, actually marking how the tree lines look like and how the sandbars looks like. Yeah. And then we're overlapping them to define the area in between 2 tree lines. We define this area, this specific zone, as recovered area, which we say 1 in the logistic regression model, and the overlapping area of 2 point bar as a non-recovered area. And so let me explain why I only pick up 15 point bar out of 27 point bar. It's because some of the point bar, they are in the less stable channel area. So within 2 decades, actually, some part of channel is already migrant. But those migrant rates is not exactly the same throughout the entire ridge. So some of the point bar actually don't have an overlapping in between 2 years, or some of the point bar just totally sort of just recover, so you don't really see them. So those are point bars we didn't select. So eventually there's only 15 of them. So once we define the recover and non-recover zones, we randomly generate 100 sample points in each zone, which end up to be 3,000 sample points for the modeling. Okay, so here I'm just really going to be super duper simple. I know there's a lot of details behind this tool modeling, but I'm just going to be super duper simple to get through this. So we apply both logistic regression model and the random forest model. And the logistic regression model, probably some of you or most of you are quite familiar with. And this is the most common used statistic model for binary dependent variables. So here's the equation: 0 as non-recovered and 1 as recovered. And then the random forest is quite popular now for the environmental studies. It is type of decision trees, machine learning modeling methods. And the basic idea behind it is these functions randomly pick up part of the samples and then run through the decision trees. And using the out-of-bag observation, throw it back to the model and to sort of compute the error metrics. So by doing this many times, they can sort of evaluate, they can sort of come out with the best model for prediction. I know this is super simple explanation, but this is basically how it works. All right, so here, really quick, here's a modeling result for the logistic regression model. So there's the 5 variables have a significant relationship with recovery, which include the distance to tree lines, flood depth, aspect, slope, and roughness. And the overall accuracy is 0.83. I would say it's pretty good. And the variance, the VIF, the variance inflection factors indicate there's no major multicollinearity issue. So let me explain this negative and positive things. I just giving one example. So the distance to 1999 tree line has a negative relationship with recovery, which means the further away from tree line, the less possibility to be recovered. All right. And so the random forest. So the way the random forest presenting their result is they provide importance values. So the overall accuracy is 0.9, which is higher than the logistic regression. So the most important variables is the distance to 1999 tree line. You can see it's in the number of 100, but please don't, I mean, this 100 doesn't mean like 100% 100. It's a relative values to each variable, other variables, but not absolute. So it's like compared to aspect, which is 0, and the distance to 1999 tree line is 100. So it's not really 100%. Okay. And so these values are relative to each other, like I say. And the slope and the roughness are also important. They are in the 70th range. And the velocity, shear stress, stream power, and the aspect, they are all having really, really low importance. And one thing I think is kind of interesting to see is the top 4 important variables are actually significant in the logistic regression model. Let me get some water. So here I just want to show some interpretation of our results. So the logistic regression and random forest modeling, I would say they're quite comparable. Like I show in the top 4, importance is actually significant. But other than the aspect, aspect is actually 0 in the random forest, but was significant in the logistic regression model. So the distance to the 1999 tree lines indicate the importance of seeding sources. So if you can see the picture A, like the video I showed you before, that most of the young growth, like new growth, is really, really close to the tree line. So we say, okay, based on the modeling, the tree line, the distance to tree line is actually quite important because they're providing seeding sources. And another thing is the slope and the roughness are both have a positive relationship with the recovery. And this basically suggests that the micro landscape help to reduce the velocity and trap seeding or organic matter, and sometimes they shelter some new growth nearby. And if you see this photo B and C we took in the field, you can see how those riparian trees trapping a lot of organic matters, even some driftwoods. And they also kind of grabbing the sediments around them. They also create relative higher elevation compared to the surrounding area. And then finally, the deeper flood water, so is negative to the recovery. So for example, whenever you have a deeper flow water, is actually lead to higher flow velocity, which is not good for the recovery. All right. Okay, take home message for the study 1. So it's a little bit repeated, but I'm going to read through this. Okay, the main purpose of the study, we want to determine what is the drivers behind the vegetation regrowth on the point bar of the study ridge, the middle ridge of Apalachicola River. And this result showing the distance to the tree line is the most important factors among others. And slope and roughness, they are associated with surface relief, which is helping to trap more organic matter and shelter new growth. And the flood depth result of the flood depths also indicate the new growth, they actually prefer area in the relative higher elevation. All right. So the continuous optical message, logistic regression and the random forest model are comparable, like I mentioned before. And I mean, the way they evaluate the model and the result they show is just sort of different. So the logistic regression model, they tell you the degrees of influence or negative, positive to the recovery. But the random forest, they do have a higher prediction rate, and they also give you this importance, the importance of the contribution of each variables or drivers to the recovery. So they're quite different, but I was very happy to see they have a quite similar results. So these modeling efforts were just like one of the first steps to quantify the dynamic point bar vegetation succession. And this outcome, well, hopefully might be able to help in the managing and restoring the Riparian corridor of Apalachicola River, or even other river in similar situation. So one of the example is, if we can maintain a forest riparian corridor, it will help the ecosystem, I mean, the entire river in a better situation. Yes, I love Bob Ross. All right, so now this is study 2. So there's an ongoing study. Actually, I'm going to present this in the CDAT, but it's basically sort of half done, but I still want to share with all of you. But please feel free to give me any suggestion about how to improve this, maybe the modeling or the analysis. So hopefully I will get more time to revise it and have a better presentation in the CDAT. All right. So this is quite interesting, like following the previous presentation I just talked about. So the more close to the vegetation, I mean the previous vegetation, tree lines, the more easy to get recover. But occasionally there's some like small new growth, which is far away. There's some small new growth is far away from the current tree lines. They occasionally established on the point bar surface, and then they survive. So this new growth continues to trap in more sediments and organic matter, and eventually they develop into an island-like feature. I'm just going to call it vegetation island on the point bar. And this vegetation island keep on growing and trapping more organic matter and getting bigger and bigger, and eventually they actually merge into the previous tree line. And that looks like a huge jump, like thinking about you have a small island, right? I'm going to show you a photo later. Thinking about you have a small island just sort of far away from the current tree line. But once it get bigger and you have the tree line also kind of keep on pushing forward to the riverside and then they merge together, then this vegetation island actually become the new front lines on the water edges. And here's a field photo with our awesome graduate student Amobi, with one of the vegetation island we find in one of the big point bar we have a field trip. So you can see the small mound beside the willow tree. That tree is a willow tree, okay. And the small mounds is relative on the downstream direction of the tree. And you can see the relative higher elevation compared to the point bar surface around it. All right. So by studying the vegetation island development, we can get some more insights about how this biogeomorphic process of vegetation regrowth on the point bar. It just, we get more information about this, and hopefully ultimately we can use this information to help for better management or any active restoration. So the main purpose, just going to keep it simple, of this study is just quantify the vegetation island growth on point bars. And we first digitize the vegetation islands on point bar, and we select 6 area photos. from 2007 to 2019. And we select this specific 6 era photos because now we have a 2-time LiDAR survey, which give you high resolution elevation information. And there's a 2 LiDAR survey in 2007 and 2018. So we kind of want to couple this elevation model, elevation information with the vegetation growth. That's why I only digitized the 2007 to 2019 vegetation islands. And we also try to determine the spatial and temporal patterns, as well as how the elevation changes between 2-time LiDAR surveys. All right, so here's the aerial photo showing a series of vegetation island developments on Point Barth. And as you can see, there's 2 more in between. So 2007, you can see there's only tiny small dots on the Point Barth. And it's continued expanding in 2013 and 2015, right? And in 2019, they actually already merged with the floodplain forest. So that is exactly what I say. They become the new front lines of the tree lines. This is actually increasing the vegetation recovery quite, more than the area have no vegetation island. So this slide is explaining how we define and digitize the vegetation island. So I'm just showing 2 photos, one in 2007, one in 2019. So on 2007 era photo, there's a tree. If there's a tree, or maybe already multiple tree, it's far away enough for more than 9 meters. I kind of come up with this value arbitrary, but you can argue with me later. So we define this as a vegetation island. In the 2019 era photos, you can see these 3 small islands. The one on the north is already merged with the floodplain forest. So I'm just going to label it as 2015 because I cannot identify any island shape after 2015. So I'm label it as 2015. And there's another 2 small islands on the south. They still kind of isolated. So I label them as 2019. So this label means the last year as vegetation island. Okay. So the idea is to identify the spatial and temporal pattern. So the first instinct is, okay, let's do some analysis, just really basic calculation. So if you see on the left-hand side, I have this hypothetical figure showing how the vegetation islands located in the middle of Point Barth at 50% distance from the upstream, right? So I have this percentage means from upstream to downstream. If you call it as 100%, and if the number is smaller, it basically means this specific island is more close to the upstream. So in ideal world, you can see if this specific vegetation islands in the middle of it, you can call it 50%. And there's a basic idea is those vegetation islands, they might prefer the area have a wider bar surface. So in that case, they kind of further away from the floodwater because those new young growth, they are quite fragile to floodwaters. So the hypothesis behind it is because it's kind of like, okay, those vegetation island, they probably prefer the area kind of far away from the water. So they want the wider bar surface area. But in reality, there's really no perfect crescent shape Point Barth. So if you see my reality shape, this is actually one of the example of the bars I digitized. It's kind of hard to couple this idea with our result. Okay, so the bar chart on the right is showing the vegetation island mostly occurs. They're around like a 40% to 80% distant from the upstream. And the 20 to 40% is the second highest. And we also make a scatter plot based on the river miles and the distance from upstream. And we color it with the last year, like I mentioned before, the last year as the vegetation islands. And for example, I have a circle. Okay, so this 3 small triangle in the figure around the river mile 55 to 60 is last as vegetation island in 2010. And they are around 50% of the distance from upstream. So far, I'm just using my eyeball methods. So the eyeball method is like, okay, I cannot really tell if there's a specific trend yet. So here's another things I want to show you. Like I mentioned before, I want to compare the elevation changes in 2007 to 2018. So I also marked the 2007 tree lines here, so you can see how much elevation increase in front of the tree lines. So there's the 2 green arrows. I'm just indicating where this vegetation island is. And they are basically fully connected with floodplain forest before the 2018 LiDAR survey. All right. Unfortunately, we only picked 11 islands out of 26 is because the 2018 LiDAR survey, whenever they do the survey, they kind of film it, well, they survey in the higher water time. And a lot of point bar, they kind of really close to water. So I cannot really get all the elevation information for 26. Well, the total number of the vegetation island I digitized is 26. So I cannot really get all of them. So there's 11 of them. But if there's a bar chart showing how the elevation changes for different point bar, I also color it with the year. And the average elevation, local elevation has increased for 1.29 meters from 2007 to 2018. And with a maximum could up to 2 meters for its elevation. And interestingly, this result is sort of comparable with one of the previous study from Cole and Brett et al. 2016. They actually study how the young riparian vegetation, how much fine sediments they can trapping. So they were giving some number like it's about 13 centimeter fine sediments per year. So if you multiply by 10, it's like 1.3 meter for a decade. So I would say quite similar. All right. Bob Ross again. Here's a very brief take-home message. The purpose of the study is we want to investigate the vegetation island developments in the middle Ecological River, and especially the vegetation island favor location in the middle and the mid-lower section of the point bars. And we did not really find a distinct spatial temporal patterns for vegetation island developments. But we might need to couple more like a point bar geometry for further analysis, like I mentioned before, the width of the point bar. And the developments of vegetation island increased the elevation of point bar with average 1.29 meter for a decade, 2007 to 2018. And one of the future direction we would like to do is I want to build maybe a machine learning modeling or other kinds of modeling to similar to the earlier presentation, like to identify the factors or the drivers behind the development of vegetation islands in Ecological River. All right, okay, thank you so much to coming to my presentation. I'm surprised actually taking longer than I thought. And here's some photos showing Ali Amobi, our awesome graduate student, come to a field trip with us several times. And we also have actually previous students helping and volunteering and riverkeeper to help for the research and study in the field. Thank you. And please feel free to give me any suggestions or questions.
Okay, question from Dr. Binford right away, the bio guy.
Yeah, Jen, in the first study, you keep using the words regeneration, recovery, regrowth, which implies that there was something there before that went away and now it's coming back. It's my understanding that point bars are depositional, and you just talked about that in the last part. as they're there. So they're basically bare sand that get colonized by pioneer species coming out. It's not a regrowth or now the river may recover from the dredging, but the point bars themselves are not recovering, are they? Really?
That's how I say recovering is they have a lot of new growth on the floodplain forest side. It's like those. So I actually I can show you this after this. I am prepared. So the channel width change. So I'm actually do the digitalization based on the tree line. That's how we say the tree. Just ignore that GIF. It's just kind of funny. So the channel width is kind of shrinking. It's because of the tree line, a kind of encroachment of the tree line to the water side. So I kind of saying, okay, this point bar is recovered because in the 1940s era photo, the channel is much more narrow compared to the channel now.
Yeah, but
the idea is those regrowth of the raptor vegetation is part of
the point bar is new ground.
Mm-hmm.
It's being colonized by pioneer species. It's not recovering. I think by using those words, you imply something you don't mean. You know, there are lots of other things to use.
Agree. Yeah, I agree. There could be something better.
Yeah, it's tricky because some of those point bars are really large because they were disposal sites. They were like new sediment, anthropogenic sediment deposits. So, yeah. But it's not regrowth if but there's like, if you could look back in time, you would see that it had vegetation before the dredging.
Yeah.
So.
We were debating about what's the best wording, like recolonization. Actually was using re-establishment, but then and there's some people comment to say it's already two decades, so establishments only happen within 3 to 5 years. So eventually I do regrowth. Yeah, it's kind of tricky.
What word do you like, Mike?
Yeah, what do you like?
Colonization, you like? Yeah.
All right, I got time to
do you know that there's some people in the human that like in the like they don't like the word colonize from the human side. So anyway, it's very tricky business.
I haven't considered about that even. All right.
Okay, Tim Fick and then Johanna.
Yeah, okay, is the speed of colonization or transformation, how's that one? Is that affected at all by the type of species? Has there been any studies about a particular species take hold, let's say, that the process of transformation or colonization, whatever you call it, regrowth, is it sped up with particular types of species and perhaps more so than others? Because I don't say anything about the types of plants or trees or, specifically that are taking root. And does that play a role at all? I'm not a physical geographer, but that's an obvious question for biology.
Right. I think it's really there's a lot of possibility, and one of the reasons why we don't really specifically mention the species because it's really hard to see if it's so most of there's like two major kind of Riparian vegetations on the point bar of the study area, basically willow and the poplar. Those are really two popular one on the point bar. So like this photo you see, I'm always sitting on, I think that's a poplar tree. And there's a one on the right hand side is a willow, and on the left hand side, that probably the poplar. And we didn't really specific compare which one is faster because well, maybe we should consider that. But yes, I mean, in the literature, there's a lot of study about poplar and the willow. Those are actually two kinds quite popular, like people try to quantify how fast they grow. I would say it's possible to do some quantification modeling for them, but like I'm doing more remote sensing, air photo approach now. So it's kind of hard to say, okay, if this specific tree is poplar or willow. Well, maybe. Yeah, get more grants. Yes.
Yeah,
you
you-
identify them now, and this doesn't change.
Yeah, although, yeah, that's an assumption, I guess, yeah. Johanna?
One
Okay.
technical point, I don't know I don't know, going on a limb here.
Go ahead.
When you're comparing your random forest model to the logistic, your logistic model didn't have a lot of those other insignificant variables in it. Sometimes when you keep these insignificant variables in a model, they pick up a couple extra percentage points of accuracy, even though they're not necessarily predicting the drivers. So those velocity, shear stress, stream power, and aspect, were those in your logistic model and kept in there, or were they tossed out because they were insignificant is the question?
Yes, whenever I do the logistic regression model, if those variables on not significant being dropped, less than 0.05. So the aspect one is actually
To truly compare the two models, then you should keep the
I get what you mean.
models in there, because they will pick up a couple of percentage. And I'm thinking that it might be 89%, and then 89 and 90, they're not significantly different from one another in terms of really what they're explaining, is my point. And so be careful with that.
Thank you.
All right, Johanna, and then that's our last question, I guess.
I know, yeah.
I have a whole lot of voice resource. So now when dredging isn't an issue anymore, do you expect the full recovery of the river? Because I know there's a lot of activities on the river in any case. For example, how do you think the river can recover given all the other activities?
So what I actually, not only the dredging, but also the dam building have some kind of effect to the entire river system. And also there's people been talking about, there's a lot of irrigation activities happening in the Georgia and Alabama side. So there's always debating. We actually have a lawsuit with Georgia and Alabama about if they should keep enough water resources for the Ecological Variable. And I mean, yes or no. One of the things I'm showing the kitty graphic is because, yes, we are always ambitious to help the Mother Nature. But one of the idea of this behind this entire study is we kind of want to know how this recovery slowly, what's the driver behind it. Like eventually we hope this entire river can get back to the original condition, but we have to know what kind of drivers behind it. Like if we do something else, is that going to hurt? Is that going to bring the good benefits to the system or not? But I don't know how long it will take for the entire river to get back to the, say, original natural status. Because there's actually, we went to one of the presentation. I went to one of the presentation with Dr. Maza, one of the scholar, Jim, he actually talking about remove the whole dams. So that would be one of the options, but it's a lot of money to remove it. But thanks for the question. I don't have a specific answer to say if the river can recover, how fast back to the original or not. Just I still need a lot of study about the whole thing. That's what I would say.
Right, but sometimes doing nothing can help, and if
Right.
the less impact you do, the better. Okay, thank you very much, Chen. We appreciate you.
Thank you for everyone coming.
Okay, and everyone in Colloquium, enjoy your break next Thursday, and see you 2 weeks